Right now, 4 separate clouds of magnetized plasma are barreling toward Earth in rapid succession, and they chose tonight to arrive. March 20th, the one night per year when Earth's magnetic shield is measurably, provably weakest. That is not a metaphor. That is orbital physics. NOAA is already calling for severe geomagnetic storms. Independent analysts are whispering G4. 2 earthquakes struck within hours of first impact, and the fringe science community is asking a question that mainstream science refuses to answer. Can the sun shake Earth? Stay with me until the end, because by the time this is over, you will never look at a clear night sky the same way again. Subscribe and follow along, because this story does not end when the last aurora fades from the sky tonight. The sun is not finished. Solar Cycle 25 still has eruptions left to fire, and the questions raised by this convergence, the stacking, the timing, the earthquakes, the signals nobody can fully explain, are not going anywhere. And when the next event arrives, this channel is where you hear it first. Without the hype and without the fear-mongering, you are going to want to be here for that. Now, let's get into it. The sun did not send a warning. It never does. Between March 16th and March 18th, 2025, our star launched what appears to be 3, possibly 4, separate eruptions of magnetized plasma directly toward Earth. Not toward the general neighborhood of Earth. Not in the approximate direction. Toward us. And right now, as you're watching this, they are already in transit. A convoy of charged particles traveling at speeds that would make any human engineering achievement look like a child's toy. Here is where this gets genuinely interesting and genuinely unsettling. The reason this event is drawing so much attention from space weather analysts isn't just that multiple coronal mass ejections were fired. It's what happens when multiple coronal mass ejections are fired in quick succession at the same target. They don't travel independently through space like separate ships crossing an ocean. They interact, they collide, they merge. The faster ones catch up to the slower ones, and when that happens, the plasma doesn't pass through. It piles up. Scientists call this process CME, cannibalization, which is one of those rare scientific terms that actually sounds exactly as dramatic as it is. The leading cloud gets consumed by the trailing one. The 2 structures merge into something denser, more magnetically complex, and potentially far more powerful than either would have been on its own. NOAA's Space Weather Prediction Center has issued an official forecast of a G2 to G3 geomagnetic storm. On the G1 to G5 scale, that sits in the moderate to strong category. Manageable, they say. Probably. But independent analyst Stephen Burns has suggested G4 conditions are on the table if these plasma clouds stack together the way the physics suggests they might. A G4 is a severe storm. The last time Earth experienced a G5, the maximum, was May of 2024. Before that, you have to go back to 2003. The first CME in this sequence was clocked leaving the sun at approximately 1,200 kilometers per second. That is fast enough to travel from Earth to the moon in roughly 5 minutes. And it has already been decelerating as it plows through the solar wind ahead of it. That deceleration is not a relief. That deceleration is precisely the problem, because it means the second and third eruptions are gaining on it. What the sun launched matters less than what those eruptions become between here and there. And right now, something is forming in the space between us and our star that no instrument has yet been able to fully see. Not every eruption from the sun is aimed at us, and that fact alone has saved civilization more times than we probably realize. The source of this particular sequence is active region 4392, a magnetically complex sunspot cluster sitting near the solar equator. The first eruption from this region fired when the active region was positioned slightly before the Earth-facing center of the solar disk. The second fired when it had rotated to slightly past center. If you're imagining the sun as a clock face, think of Earth direct as 12 o'clock. These eruptions launched from roughly 11 and 1 respectively. That is, in the language of space weather forecasting, an uncommonly clean alignment. There's a meaningful difference between a glancing blow and what researchers call a full envelope hit. A glancing blow clips the edge of Earth's magnetosphere. You get some activity, maybe some aurora at higher latitudes, and then it's over. A full envelope hit means Earth sits inside the main body of the plasma corridor. The entire structure washes over the magnetosphere from multiple angles simultaneously. The WSA Enlil model, which is the primary solar wind forecasting tool used by NOAA, places Earth well inside the central corridor of this event's trajectory. Not on the edge, not in the outer band, inside it. What makes the geometry even more notable is the ecliptic plane alignment. Without turning this into an orbital mechanics lecture, the ecliptic is essentially the flat plane in which Earth orbits the Sun. CMEs that travel along this plane hit us differently than ones that travel above or below it. These eruptions are traveling along it. Earth isn't just in the path horizontally. The vertical spread of the plasma structure also encompasses our position. In plain terms, we are not going to be clipped. We are going to be engulfed. Here's something worth sitting with for a moment. The two primary eruptions actually skewed in slightly different lateral directions when they launched, and yet both are still Earth-directed. The geometry is almost insultingly precise. You'd think with all the space between here and the Sun, that's 150 million kilometers, give or take, there would be more room to miss. There isn't. Not this time. But even a direct hit, even a perfectly aimed full envelope impact, doesn't automatically mean a catastrophic storm. The intensity of what we feel depends on something that changes between launch and arrival, something we cannot measure until it's almost too late to matter. Something unusual appeared in the tracking data for the first coronal mass ejection in this sequence, and space weather analysts noticed it almost immediately. It was running late, approximately 12 hours behind the expected arrival window. In the context of space weather forecasting, a 12-hour delay is not a minor rounding error. It is a significant deviation that changes the physics of everything that follows. When a fast-moving object in space slows down, everything behind it begins to close the gap. The second and third eruptions, launched with considerably more velocity, are now traveling into a corridor that the first CME has already partially carved, but has not yet fully cleared. The result is compression. Magnetized plasma behaves in ways that feel almost counterintuitive if you're used to thinking about gases or liquids. It doesn't slip through itself cleanly. It is, in a sense, sticky. When the leading CME slows and the trailing one catches up, instead of one passing through the other, they compress against each other. The plasma piles up. The magnetic field lines tangle. The structure that emerges from this collision is denser than either individual cloud, and its internal magnetic configuration becomes something that no model launched before arrival could have fully predicted. This matters enormously because the geomagnetic impact of a solar storm is not primarily a function of speed or even total particle count. It is a function of the magnetic structure inside the plasma cloud, specifically, which direction the magnetic field lines are pointing when the storm arrives at Earth. And when two clouds merge in transit, their individual magnetic structures combine into something new, something neither one would have produced alone. Think of it like a highway at rush hour. One slow car isn't dangerous, but when traffic piles up behind that slow car, the energy stored in all those moving vehicles gets concentrated into a smaller and smaller space. The slow car doesn't speed up. The cars behind it don't stop. The collision isn't guaranteed, but the probability climbs with every passing minute. Right now, the second and third CMEs in this sequence are the cars that haven't braked yet. The honest answer from the modeling community is that what we're seeing exceeds the clean, tidy scenario that standard forecasting is calibrated for. This is a messy event, a complicated event, and behind the already merged, already compressed leading structure, there is something else in this convoy that most of the coverage has almost entirely ignored. Let's talk about the thing that hasn't been getting enough attention, because it might be the detail that pushes this event from notable into genuinely significant. Trailing behind the coronal mass ejections, timed to arrive somewhere around March 21st or 22nd, is a coronal hole high-speed stream. A coronal hole is exactly what it sounds like, a region of the sun's outer atmosphere where the magnetic field opens outward instead of looping back, allowing solar wind to escape at dramatically higher speeds than normal. The solar wind flowing from this particular coronal hole is expected to reach velocities approaching 700 kilometers per second. For reference, typical solar wind cruises along at around 400 kilometers per second. This is nearly twice that. Now, a high-speed stream on its own is rarely a major story. It can cause minor geomagnetic disturbances, some elevated aurora activity, nothing catastrophic. But a high-speed stream that arrives immediately after a sequence of coronal mass ejections is a fundamentally different situation. Here's why. Between the fast-moving stream and the slower ambient solar wind ahead of it, a structure forms called a co-rotating interaction region, or CIR. Think of it as a compression wall, a boundary where fast-moving solar wind rams into slow-moving solar wind, and the pressure builds up along that boundary like a wave building before it breaks. When that compression wall arrives and interacts with a magnetosphere that is already stressed and recovering from CME impacts, the combined effect can extend and intensify the geomagnetic storm in ways that neither the CMEs alone nor the stream alone would produce. Historical data on multi-driver storms, events where CMEs and high-speed streams overlap, consistently shows that these combinations outperform single-driver storm forecasts. Not always dramatically, but often enough to matter. So the full picture looks like this. A merged, compressed plasma structure from multiple CMEs arrives and begins battering the magnetosphere. And then, just as the initial storm would normally be winding down, a fresh surge of high-speed solar wind arrives to reinforce it. Wave 1, Wave 2, and then a third push from behind. All of it compounding, all of it layering, all of it arriving in a window of roughly 48 to 72 hours, and all of it arriving on the one night of the year when Earth's magnetic field is least prepared to resist it. March 20th is the spring equinox, and that is not a coincidence worth dismissing. There is a phenomenon in space physics called the Russell-McFerrin effect, named after the two researchers who identified it in 1973, and it explains why geomagnetic storms are statistically nearly twice as common in March and September as they are in the middle of summer or winter. The effect comes down to geometry, specifically the geometry of Earth's magnetic axis relative to the incoming solar wind during equinox periods. Here's the simplified version. Earth's magnetic axis is tilted relative to the plane of its orbit around the Sun. During the equinoxes, that tilt puts Earth's magnetic field in a configuration where it aligns more favorably with the southward-oriented component of the solar magnetic field. And when the two align in opposite directions, Earth's northward field facing the Sun's southward field, something called magnetic reconnection, happens at the boundary between them. The solar wind's magnetic field lines essentially link up with Earth's field lines and rip open a door, allowing energy and charged particles to flood into the magnetosphere far more efficiently than they could at other times of year. The data on this goes back to 1932. Analysis of storm frequency from 1932 through 2014 consistently shows the equinox windows as the peak periods for geomagnetic activity, even accounting for variations in solar output. The equinox doesn't create storms. The sun creates storms, but the equinox amplifies them. The same solar event that produces a G2 storm in July might produce a G3 or G4 storm on March 20th. The incoming energy is the same. What Earth does with that energy is not. March 20th, 2025 sits directly in the most sensitive window of this effect. The CMS arriving tonight are not arriving during an average period of Earth's vulnerability. They are arriving during the annual peak. And this amplification only gets interesting, or alarming, depending on your disposition, when you factor in the one variable that no model can predict until it literally arrives at your doorstep. Everything you've heard so far, the stacking CMEs, the coronal hole stream, the Equinox amplification, all of it is secondary to one factor that determines whether this event becomes a footnote or a headline. That factor is the orientation of the interplanetary magnetic field embedded inside the incoming plasma. The interplanetary magnetic field, or IMF, permeates the solar wind and the plasma clouds that travel with it. It has a direction, it points either northward or southward, or somewhere in between, and that direction fluctuates. When it points northward, the interaction with Earth's magnetic field is relatively weak. The energy of the incoming storm is partially deflected. But when it points southward, what scientists call a negative BZ condition, the door opens. Magnetic reconnection accelerates. Energy pours into the magnetosphere with remarkable efficiency. The storm intensifies. And the longer that southward orientation persists, the deeper and more sustained the geomagnetic disturbance becomes. A fast CME with northward BZ can arrive and produce almost nothing. A slower CME with strongly southward BZ can produce a severe storm. Speed matters. Density matters. But BZ is the deciding variable, and it is also the one variable that cannot be reliably predicted until the plasma structure is close enough to measure directly, which typically means about 30 to 60 minutes before impact. When multiple CMEs merge in transit, their individual magnetic field orientations combine into a structure that is, essentially, a mystery until it arrives. The individual clouds had their own BZ characteristics when they launched. The merged structure has new ones that emerged from the collision. Models can approximate. Models cannot confirm. And if the merged structure carries a prolonged southward BZ, if the field stays pointed in the wrong direction for hours rather than minutes, the Equinox amplification that was already in play kicks into overdrive. This is the single biggest uncertainty in the entire forecast. Not the speed, not the density, not the timing. The orientation of a magnetic field inside a plasma cloud that is currently somewhere between the Sun and Earth, and that no instrument in existence can currently see in any detail. Some researchers are watching one additional factor in the timing of this alignment, something that hovers at the boundary between data and speculation, and it involves the moon. A new moon occurred in the days immediately preceding this event, and while that statement might seem more appropriate for an astrology channel than a space weather analysis, bear with me for a moment, because the fringe science community has latched onto this timing for reasons that are at least physically coherent, even if they remain entirely unproven. The moon exerts tidal forces on Earth. That is not fringe science, that is introductory physics. The tidal influence of the moon affects Earth's oceans, its crust to a measurable degree, and its ionosphere. During a new moon, when the moon sits between Earth and the Sun, the gravitational alignment produces what are called spring tides, the strongest tidal forces of the lunar cycle. Some researchers have noted correlations, not proven causation, between enhanced tidal periods and slight increases in seismic activity, or between lunar phase and atmospheric electrical phenomena. A partial solar eclipse was also observed from orbit during this window, adding another layer to the geometric alignment argument. The more speculative extension of this idea involves electromagnetic coupling, the notion that the tidal stretching of the ionosphere during a new moon might make it marginally more susceptible to the kind of electrical stress that an incoming geomagnetic storm produces. The Earth ionosphere system behaves in some models like a capacitor, two conductive layers separated by an insulating atmosphere, with electrical potential stored between them. If tidal forces are already perturbing that system when a major storm hits, some researchers argue the combined stress could exceed what either influence would produce independently. It is worth being absolutely clear that there is no strong scientific consensus supporting this connection. The correlations that have been documented are weak, contested, and not reproducible across all datasets. This is a pattern that some researchers are exploring, not a mechanism that science has confirmed. But the timing here, a new moon, a partial solar eclipse observed from orbit, and a multi-CME stack arriving during the equinox, is the kind of clustering that makes certain kinds of minds start drawing circles on whiteboards. Whether those circles represent real connections or human instinct toward pattern recognition is a question that will come back to haunt us before this video is over. For now, what is not speculative is the broader context in which all of this is unfolding. The Sun operates on an approximately 11-year cycle of activity, moving from solar minimum when the surface is relatively quiet, sunspots are rare, and eruptions are infrequent, to solar maximum when the surface becomes a churning environment of magnetic complexity, daily flares, and frequent coronal mass ejections. We are currently in solar cycle 25, and we are at or very near the transition point between maximum activity and the beginning of the gradual decline back toward minimum. This phase is, in some respects, the most energetic and unpredictable part of the cycle. The frequency of M-class flares, the mid-range, energetic flares that often accompany significant CMEs, has been elevated for the past 18 months. Occasional X-class flares, the most powerful category, have punctuated the cycle with reminders that solar cycle 25 is performing at or above the predictions that space weather scientists made for it at the start of the decade. The solar physics community initially expected cycle 25 to be moderate. It has been more active than that, and we are still not fully past the most energetic phase. What this means practically is that the event unfolding right now, multiple CMEs launched in rapid succession from a complex active region, is not an anomaly within this cycle. It is a characteristic behavior of where we are in the 11-year pattern. The Sun is doing what a sun near solar maximum does. It is doing it repeatedly. It is doing it in clusters, and it will continue doing it in the coming months as the cycle slowly winds down. History shows that the transition from maximum toward minimum is not a clean, linear decrease in activity. There are often late flurries of significant events, the Sun's last surges before the quiet returns. The events of March 16th through March 20th, 2025, will not be the last sequence of this kind. They may not even be the most significant sequence of this kind before the cycle ends. But they are arriving in a convergence of factors, stacking plasma, equinox amplification, lunar phase, compressed timelines, that makes this particular cluster worth paying very close attention to. And when these stacked eruptions finally reach Earth, they don't arrive all at once. The arrival of this event is not a single moment. It is a sequence, and understanding the sequence matters if you want to understand why this storm could feel different from a typical one-and-done geomagnetic event. The first wave belongs to the March 16th coronal mass ejection, the leading structure, the slower one, the one that has been decelerating as it plows through the solar wind. This is the initial shock, the first compression of Earth's magnetosphere, the opening pressure. Behind it, somewhere in the gap between the two primary eruptions, sits the merged structure, the result of the March 18th CME and associated filament material catching up to and partially consuming the first cloud. That merged structure carries its own shock front, its own density profile, its own magnetic configuration. It arrives not as a separate clean event, but as a second surge of pressure into a magnetosphere that has not yet fully recovered from the first. Geomagnetic storms have phases. There is the initial phase, when the shock front first compresses the dayside magnetosphere, and you see a sudden jump in geomagnetic indices. Then comes the main phase, when southward BZ conditions allow energy to pour in, and the storm indices drop sharply, the signature that scientists look for to classify storm severity. And then the recovery phase, which can take anywhere from hours to days as the magnetosphere slowly reassembles itself. In a single CME event, these phases follow each other in sequence. In a multi-CME event like this one, the recovery phase of the first impact gets interrupted by the initial phase of the second. The magnetosphere never gets the breathing room it needs to stabilize. The storm doesn't spike and recover. It rolls. Peak activity is expected sometime around March 20th through 21st. The equinox window and the trailing high-speed stream could keep geomagnetic indices elevated well into March 22nd or 23rd. That is potentially 72 hours of sustained geomagnetic disturbance, with multiple intensity peaks rather than one. And the most visible consequence of all that energy input is also, paradoxically, the one that is easy to forget is a symptom of something extraordinary happening overhead. The aurora is not magic, though it is forgivable for thinking so the first time you see it. What it actually is a symptom. When the magnetosphere is compressed and energy floods in through the polar cusps, the points on Earth's magnetic field, where the field lines converge at the poles, charged particles follow those lines down into the upper atmosphere. At altitudes of roughly 100 to 300 kilometers, those particles collide with oxygen and nitrogen molecules, exciting them to higher energy states. When the molecules return to their normal state, they release that energy as light. Green from oxygen at lower altitudes, red from oxygen at higher altitudes, blue and purple from nitrogen. The specific colors you see depend on the altitude of the collisions and the intensity of the particle stream driving them. Under normal conditions, say a G1 storm, aurora is visible from northern Canada, Scandinavia, and similar high-latitude locations. Under G2 and G3 conditions, the oval of visibility expands equatorward. The model suggests that a sustained G3 event from this sequence could push aurora visibility to latitudes as far south as Illinois in the United States, roughly 42 degrees north latitude. That means large portions of the northern continental United States, Central and Northern Europe, and parts of Asia could be looking up at a sky they would not normally expect to light up. If the storm strengthens toward G4 conditions, that oval expands further still. What makes this event particularly interesting for aurora observers is the multi-night potential. Because the storm is structured in waves rather than as a single peak, there may be aurora activity on consecutive nights rather than a single dramatic display followed by silence. Each time a new pressure surge arrives, the particle injection into the polar regions resets. The sky doesn't just light up once and go dark. It lights up, dims, and potentially lights up again. That is beautiful, and it is also the most publicly visible evidence that something genuinely unusual is happening to the electromagnetic environment of the entire planet. While the sky puts on its show, however, certain systems we depend on every single day are quietly beginning to struggle. Geomagnetic storms do not announce themselves with alarm sirens. Their effects on the infrastructure of modern civilization are, for the most part, subtle, technical, and entirely invisible to anyone not specifically looking for them. The first category of impact involves satellites. Earth's upper atmosphere expands when it absorbs energy from a geomagnetic storm. That expansion increases atmospheric drag on satellites in low Earth orbit, the same orbital band where thousands of operational spacecraft, including the bulk of the Starlink constellation, maintain their positions. Increased drag means increased fuel consumption for station keeping, And in extreme cases, it means orbital decay, satellites dropping into lower orbits faster than planned and requiring earlier replacement. During the May 2024 G5 storm, operators reported measurable drag increases across multiple satellite networks. A G3 or G4 event in this sequence would produce similar, if less extreme, effects. The second category is GPS. The Global Positioning System relies on extremely precise timing signals, traveling from satellites to receivers. And the ionosphere, the electrically charged upper layer of the atmosphere, is the medium those signals must pass through. During geomagnetic disturbances, the ionosphere becomes turbulent and non-uniform. Signal paths bend unpredictably. Timing accuracy degrades. For most consumer GPS applications, navigation, delivery routing, the errors are minor annoyances. For applications that depend on centimeter-level precision, like precision agriculture, autonomous vehicle systems, or certain aviation approaches, the degradation can be operationally significant. High-frequency radio communications, still used extensively by aviation and maritime operations, face degradation or complete blackout on transpolar routes during major storm events. Airlines routinely reroute polar flights during geomagnetic storms, adding hours and fuel costs to intercontinental journeys. Power grids at high latitudes are susceptible to geomagnetically induced currents, electrical currents that the storm's effects drive through the ground itself and into the conductive infrastructure of transmission lines and transformers. The 1989 Quebec blackout, which left 6 million people without power for up to 9 hours, was triggered by a G5 event. A G3 typically produces manageable fluctuations rather than catastrophic failure, but grid operators in Canada and Scandinavia will be watching their systems carefully tonight. And behind all of these practical concerns, scientists will be watching for something specific in the real-time data, a signature that tells them whether this event is behaving the way the models suggest, or whether the stacking process has produced something the models didn't anticipate. There is a satellite sitting at a gravitationally stable point between Earth and the Sun, approximately 1,500,000 kilometers from our planet, positioned at what is called the L1 Lagrange point. The mission is called DSCO-VR, the Deep Space Climate Observatory. Its job, among other things, is to serve as the solar wind monitoring station for Earth, the first instrument that can take a direct measurement of what is actually inside an incoming CME before it hits our magnetosphere. When the leading edge of this event reaches DSCO-VR, scientists and forecasters will be watching for a very specific set of signatures in the data. They will be looking for sudden jumps in solar wind density, indicating the compressed, merged plasma structure has arrived. They will be watching solar wind velocity. A rapid acceleration in speed indicates a shock front passage, the leading edge of the main storm material. And they will be watching, above everything else, the BZ component of the interplanetary magnetic field. The moment that number goes negative, the moment the field swings southward, the clock starts. Here's the thing about that warning. It gives Earth approximately 30 to 60 minutes of advance notice before the storm makes contact with the magnetosphere. 30 to 60 minutes is enough time for grid operators to take defensive measures. It is not enough time for most other systems to meaningfully adapt. It is certainly not enough time to avoid what's coming. It is simply enough time to brace. If DSCO-VR shows a prolonged negative BZ, hours of southward field, not minutes, the forecasters will revise upward. If it shows a complex, mixed polarity field oscillating between north and south, the storm will be difficult to characterize in real time. If the merged structure carries the signature of stacked, compressed plasma, elevated density sustained over a longer period than a typical single CME, that confirms the cannibalization process produced exactly what the physics predicted it would. This is the moment of truth for every uncertainty that has been building in this forecast since the first flare launched on March 16th. And here is the genuinely strange part. While scientists were watching that data in real time, while the first signatures of this event were beginning to register, something happened on the surface of the Earth itself that set off a very different kind of alarm. Within approximately a 2-hour window on March 20th, 2025, two significant earthquakes occurred in different corners of the planet. The first was a magnitude 6.6 event near the South Shetland Islands, off the Antarctic Peninsula. The second was a magnitude 6.1 event in Vanuatu, in the southwestern Pacific. Two separate tectonic regions, two separate fault systems. No geological relationship between them whatsoever, and yet they struck within hours of each other, on the same day as the spring equinox, and within the arrival window of the first coronal mass ejection impacts. The South Shetland Islands event is worth pausing on for a moment. The Antarctic region is not a seismically quiet zone. The Scotia Arc, which includes the South Shetland Islands, sits at a complex convergence of tectonic plates and experiences regular seismic activity. But a magnitude 6.6 event with a reported focal depth of approximately 5 kilometers is relatively shallow, and shallow earthquakes release their energy more efficiently at the surface than deep ones. The Vanuatu event sits in one of the most seismically active corridors on Earth, the Pacific Ring of Fire, where magnitude 6+ events are not rare. Taken individually, neither of these earthquakes would generate any particular scientific concern. Taken together, on this specific day, in this specific window, with the online community already watching the space weather situation in real time, the reaction was immediate. The fringe science forums and the mainstream space weather discussion boards briefly overlapped in a way they rarely do. Because officially, according to every major geological institution, there should be no connection between what is happening in the solar wind and what happens on the tectonic plates beneath our feet. The consensus position on this is clear, and it is worth understanding exactly why before we go further. The United States Geological Survey has a position on the relationship between solar activity and earthquakes, and that position is consistent with the broader scientific consensus. There is no demonstrated, consistent link between solar cycles and seismic activity. The USGS notes that statistical analyses attempting to find a predictive relationship between geomagnetic storm intensity and earthquake frequency have not produced findings robust enough to support a causal connection. Earthquakes are driven by tectonic stress, the slow accumulation of strain along fault boundaries as plates move relative to each other. That stress builds over months, years, decades, and centuries. When it exceeds the frictional strength of the fault, it releases. The timing of that release is governed by the internal mechanics of the fault system, not by what the sun is doing on any given day. The statistical baseline is also relevant here. Earth experiences approximately 10 to 15 magnitude 6 or greater earthquakes every single month. That averages out to roughly 1 every 2 to 3 days. On any given day, when something significant is happening in space weather, there is a reasonable base rate probability that a significant earthquake will also occur somewhere on Earth, not because of any connection, but because significant earthquakes are simply not rare events. This is the baseline the mind tends to forget when it is primed to look for patterns. Clustering of earthquakes can and does occur naturally. Stress redistribution from one event can trigger subsequent events in the same region or along connected fault systems, but not in geographically disconnected regions like Antarctica and Vanuatu. The clustering observed here does not fit the pattern of tectonically related aftershock sequences. And yet, some recent research suggests the conversation may not be entirely closed. What follows is clearly labeled as hypothesis, not established science, not consensus, but research at the frontier of a contested and not yet resolved question. A team associated with the University of Tsukuba in Japan published work suggesting a potential indirect mechanism by which solar activity could, over the course of weeks to months, influence seismic probability. The proposed pathway goes roughly like this. Elevated solar radiation, particularly during active solar periods, influences water cycle dynamics in the upper atmosphere. Increased energy input alters precipitation patterns, which changes the volume and distribution of water in the crust. And in tectonically stressed fault systems, changes in pore pressure, the pressure exerted by fluid inside rock, can alter the critical threshold at which a fault slips. Water effectively lubricates faults. Changes in pore pressure can lower or raise the threshold for rupture. The mechanism is physically coherent, measurable in principle, and consistent with known fault physics. But the proposed time delay, weeks to months, not hours, creates an immediate problem for explaining the timing we just saw. More on that shortly. The second proposed mechanism is more direct and considerably more speculative. Some researchers have explored the concept of ionospheric capacitive coupling, the idea that the Earth ionosphere system, behaving as an electrical capacitor, can transmit stress through the crust. Solar storms increase the electrical loading of the ionosphere. If the Earth ionosphere capacitor experiences a surge in electrical potential, some models suggest that stress could propagate downward into the conductive materials of the upper crust and concentrate in regions already under tectonic strain. The stress levels involved in this mechanism are estimated to be comparable in magnitude to tidal forces, which are themselves studied as potential earthquake triggers. The 2024 Noto Peninsula earthquake in Japan occurred during a period of elevated geomagnetic activity, and some researchers flagged the timing, though without claiming certainty. These are not proven mechanisms. They are not endorsed by the mainstream geophysical community. They are hypotheses, internally consistent physical arguments that have not survived the full scrutiny of rigorous peer review and independent replication. The reason they keep appearing in the literature is that the question keeps nagging at researchers who look at the timing correlations without being satisfied by pure coincidence. But even these hypotheses carry a problem that the earthquakes on March 20th expose immediately. Here is the problem that the proposed mechanisms face when confronted with what actually happened on March 20th, and it is a problem worth taking seriously rather than glossing over. Both major hypotheses for a solar seismic connection involve a time delay. The pore pressure mechanism operates over weeks to months. Solar energy enters the water cycle, redistributes groundwater, alters fault pressure, and eventually contributes to a rupture. That is not a same-day effect. The ionospheric coupling mechanism, while faster in principle, is still modeled as a gradual process of electrical stress accumulation rather than an instantaneous trigger. And yet the earthquakes on March 20th occurred within the same narrow window as the first CME impacts. Not days later, not weeks later. Essentially simultaneously, on a geological timescale. This creates three interpretive options, and none of them is entirely comfortable. The first is simple coincidence. The earthquakes happened on this day because earthquakes happen every few days regardless, and the overlap with the storm window is a product of human pattern-seeking behavior rather than physical reality. That is the most scientifically defensible position, and it may well be the correct one. The second is that some faster mechanism exists, one that neither the pore pressure model nor the ionospheric coupling model captures, that can transmit solar storm energy to tectonic systems on a timescale of hours rather than weeks. That would require a new mechanism, and new mechanisms require extraordinary evidence. The third possibility is more uncomfortable still, that the correlation is real but not causal, that some other factor, something in the broader state of the solar terrestrial system during this specific convergence of conditions, is influencing both solar activity patterns and tectonic release patterns through a pathway that current science has not yet mapped. What we are left with is a genuinely unresolved question, and unresolved questions, by their nature, open into something larger. There is an idea that circulates on the margins of space physics and Earth system science, and it goes by different names in different communities, but the core concept is always the same: that the sun, the solar wind, the magnetosphere, the ionosphere, the atmosphere, and the solid Earth are not separate systems that occasionally interact. They are components of a single, coupled system, continuously exchanging energy through pathways that mainstream science tends to study in isolation. The global electric circuit is the most scientifically grounded version of this idea. It describes a continuous flow of electrical current from thunderstorm systems in the lower atmosphere up to the ionosphere and back down again through fair weather regions. A planetary-scale electrical circuit driven by convective weather and closed through the ionosphere. This circuit is real. It is measured. What is less settled is the degree to which solar inputs at the top of the system, geomagnetic storms injecting energy into the ionosphere, propagate downward through this circuit and influence systems at lower altitudes. Some researchers have proposed that tropical cyclone intensification correlates with periods of elevated geomagnetic activity, suggesting that the additional electrical energy flowing through the global circuit during storms could influence the convective dynamics of large weather systems. This is speculative and not accepted in mainstream meteorology, but the physical argument is not incoherent. If the global electric circuit is a real pathway for energy exchange between the upper and lower atmosphere, then events that substantially perturb the top of that circuit, like the geomagnetic storm currently in progress, might produce measurable effects further down the chain. The appeal of this unified model is obvious. Instead of a collection of unrelated coincidences, solar storm, earthquakes, unusual atmospheric phenomena, it offers a single framework in which all of these observations are symptoms of the same underlying energy flow. It is intellectually satisfying in the way that grand unified theories always are. The problem is that intellectual satisfaction is not the same as scientific validity, and the evidence for most of the specific claims within this framework ranges from thin to non-existent. But then there are the signals that don't fit easily into any explanation, confirmed, measured, and yet deeply confusing. The Schumann resonances are electromagnetic resonances that exist in the space between Earth's surface and the lower ionosphere, a cavity, essentially, bounded below by the conducting ground and above by the conducting ionosphere. Lightning unexplained deviations in the resonance record are not unprecedented, and they are not automatically meaningful. Local thunderstorm activity, instrument calibration issues, electromagnetic interference from nearby sources, even solar radio bursts can all produce anomalous readings that look dramatic and are ultimately mundane. And critically, these anomalous signals were not universally replicated at other monitoring stations during the same window, which is the first thing any serious researcher would look for. The reason these signals attract attention beyond the technical community is partly their timing, and partly something that feels almost too convenient to mention in a science video without extensive qualification. The frequencies flagged in the anomalous data overlap with the range of human brainwave activity. Alpha waves associated with relaxed wakefulness occur between 8 and 12 Hz. The 14 Hz range sits in the low beta band. Some researchers in the highly speculative field of bioelectromagnetics have proposed that human neurological systems could be subtly influenced by disturbances in the Schumann resonance, a notion that mainstream neuroscience regards with considerable skepticism. The overlap in frequencies is interesting. It is not evidence of a connection, but it is the kind of detail that tends to travel fast in certain communities, and it is worth naming it clearly while also being equally clear about what it is not. Before we pull all of these threads together, it is worth spending some time with the most important cognitive tool you can bring to events like this one, because it is the tool that separates careful thinking from pattern obsession. Human beings are, at a fundamental level, pattern recognition machines. This is an evolutionary advantage. It is also a persistent source of error. Our brains are specifically calibrated to find signal in noise, to identify structure in randomness, and to generate meaning from coincidence. We are so good at this that we do it even when there is no pattern defined, and we do it especially when we are primed by expectation. If someone tells you that solar storms cause earthquakes, and then 2 earthquakes happen during a solar storm, your brain does not experience that as a coincidence. It experiences it as confirmation. The statistical baseline matters here, and it is worth repeating. Earth experiences a major earthquake, magnitude 6 or greater, approximately once every 2 to 3 days. On any day when an unusual space weather event is occurring, there is a reasonable probability approaching certainty that a notable earthquake will also occur somewhere on the planet. If you are already paying attention to the space weather event, that earthquake will feel significant. If you are not paying attention to space weather that day, that same earthquake will be a geological footnote that you scroll past in the news feed without registering. This is sometimes called the Texas sharpshooter fallacy. You fire bullets at a barn wall, draw a circle around the tightest cluster, and announce that you hit the target. When we select dramatic coincidences for attention and ignore the vast background of equally dramatic coincidences that don't align with our narrative, we are drawing circles around the bullets after they've landed. The equinox, the earthquakes, the Schumann resonance anomaly, the new moon, these all happened. Whether they are connected or coincident is a question the data has not answered. And yet, with that honest caveat fully acknowledged, events like this keep presenting the same clustering that refuses to feel entirely random. So, here is where we actually stand tonight. Multiple coronal mass ejections, launched between March 16th and 18th, merged in transit and arrived at Earth during the spring equinox, the annual window of peak magnetic vulnerability. A coronal whole high-speed stream is following behind them, extending the geomagnetic disturbance window, potentially into March 23rd. The official forecast says G2 to G3. Independent analysis says G4 is plausible. Aurora is expanding across middle latitudes. GPS is degraded. Grid operators at high latitudes are watching their systems. Satellites in low Earth orbit are burning slightly more fuel than usual to maintain position. 2 magnitude 6+ earthquakes struck within hours of each other on the same day as the first CME impacts. One near Antarctica, one in the southwestern Pacific. The USGS says coincidence. Some researchers point to physically coherent but unproven mechanisms that might link the two phenomena. The timing mismatch between those mechanisms and the observed simultaneous occurrence remains unresolved. Schumann resonance monitoring stations recorded anomalous signals during the event window. Those signals were not universally replicated. Their cause remains unclear. You have, at this point, 2 available interpretations. In the first, these events are independent. The Sun fires CMEs. The equinox amplifies them. The geomagnetic storm unfolds exactly as expected, and the earthquakes are a statistical certainty that coincided with unusual space weather, because significant earthquakes coincide with everything. They happen every 2 to 3 days, regardless of what the sun is doing. The Schumann anomaly is instrument noise or local weather. The new moon is background. The pattern is a projection. In the second interpretation, these systems are not as independent as current mainstream science assumes. The energy flowing from the sun through the magnetosphere into the ionosphere and downward through the global electric circuit is not a clean, modular chain of isolated effects. It is a cascade, and the Earth at the bottom of that cascade is more responsive to what happens at the top than the dominant scientific framework currently accommodates. What makes this genuinely difficult is that neither interpretation can be fully dismissed with the evidence currently available. The mainstream position is not wrong to demand stronger evidence before accepting a novel causal connection. The fringe position is not wrong to note that the historical record of correlations is persistent enough to deserve continued investigation. The honest position is that we are watching an event unfold in real time at the intersection of established science and open questions, And the most intellectually honest thing anyone can say about the earthquake timing is, we don't know. What we do know is that solar cycle 25 is not done. The active region that launched these eruptions has rotated partially away from Earth direct, but other active regions are developing. The Sun at or near maximum is a system in a state of frequent energetic release, and the pattern of clustered CME events, stacked plasma structures, and enhanced geomagnetic activity is not going away. In the coming months, there will be more events, more opportunities to watch the cascade, more data points to either strengthen or dissolve the correlations that nights like this one generate. We may already be inside the answer. Living through it, measuring it in real time, accumulating the data that will eventually tell us whether these systems are truly independent or quietly, invisibly coupled in ways that science is only beginning to find the vocabulary to describe. The question isn't whether the sun can shake the earth. The question is whether we have been looking closely enough, long enough to know.